Not much these days. All right, so 2.5. Oh, by the way, when you get to the test, actually, I'll wait to talk about this at the end because I want to talk about all test stuff at once. So, free fall. Concept of free fall means what? Just give me a general idea. Tristan. An object is dropped and falls toward the ground. Great. What's the only thing it's... Good. Only gravity acts on it. That's the concept of free fall. Only gravity acts on it. Now, in this course, what are we going to start to incorporate also? Air resistance. Okay? We're going to see how air resistance also plays a role in this problem. We're going to look at that probably in like chapter 4 or 5 when we get to forces. Because then we're going to start looking at the force of drag or air resistance. And we're going to see that that's actually what's called a differential equation. It's a function of our velocity. And I don't know if Mr. Dominic may have talked about this. I didn't go over it in my course last year, but the faster you move, the more air resistance you feel. It's a function of your velocity, it turns out. Its F is proportional to V squared. So if you double your velocity, you feel 4 times as much air resistance, etc. And we'll get into more of that, but I don't want to jump ahead. But for free fall, for the concept of chapter 2, we don't have to worry about air resistance. So on tomorrow's exam, on Friday's exam, whenever a problem is given, unless I state that there is air resistance, the assumption is that there is not air resistance. Okay, a problem, even on the AP exam, will do the same thing. It will specifically mention air resistance if that should be taken into account in your answer. It will specifically mention air resistance if it should be taken into account. If not mentioned, the assumption is it doesn't exist. There is no air resistance for that part. Okay, so for free fall, all I'm going to do is go through an example so we get an idea of what you could expect. Okay, so we already know this idea that if two objects are dropped, no matter what they are, let's say a sheet of paper on the right and the ball on the left, they will fall at equal rates. And what will happen to those spaces is that they will increase. Why are the spaces from time equals 1 to time equals 2 increasing? What's happening physically? Spence? They are accelerating. So you'll notice that the gap from second to second will never be consistent for an object that is accelerating. What does this graph look like on an XY plane, or on a Cartesian coordinate, I should say, not XY, really. On a Cartesian plane. Parabola. Yeah. It's a parabola, actually, right here, right? This is what it looks like. It's a parabola looks like that. It's the first half, or the right half of the parabola. Okay, it's increasing its position at an accelerated rate, therefore the gaps get bigger. Anybody know, I forget what this is called, I really forget, and Mr. Dominic, I think, might have talked about it last year. There's a phrase for this where you can see like a timestamp of an object at different things along the way. There's an old physics term for it. Did you use that phrase last year? Like a time ticker or a tape ticker or anything like that? Does that ring a bell? There's a phrase for it. There's a phrase for it where, anyway, because it might come up in the AP exam, I'll look at the terminology. There's an older device that was used, and what would happen was it would be like a spool of paper, and that spool of paper would be moving, and every once in a while a dot would be placed on it, and that dot would be the position of the object, and it would somehow correspond to where it was in the air. And you would see that the spacing out of the dots kept increasing on the little device. There's a phrase for it. I'll go with it, but that's what I'm trying to show here. What is it? Is that what it's called? I don't know if I was using the right word. I think I was just using what I thought it was. I can Google it after. But the idea is that, again, if you were to take a freeze frame every second along the way, the gap is going to keep getting larger. Okay, it's going to keep getting larger. What's the gravitational constant? Good, 9.81. We're going to use G equals, and I think on the sheet it says 9.8, so we'll stick with that to be consistent. If you look at your formula sheet. I will have formula sheets for you on the test. You do not have to memorize, but keep in mind that there weren't too many formulas this chapter anyhow. All right, the formula sheet is on Moodle, so you can get an idea what it looks like. If we're looking at free fall motion where it's falling downward, our acceleration is what kind of a value? What kind of a value, Matt? It's negative, okay? So when it's falling downward, we're looking at G is equal to negative 9.81. I'm sorry, negative 9.8. I got to stop saying the 1. And I could call this AY. I had a tendency to do that last year, and I think it is a good thing to do when we start to look at projectiles, because we're going to look at the X and the Y directions separately. Okay? So we can call that AY when it's falling down. But G in general is 9.8. Okay? When we use forces, we'll notice that G is positive. When we use kinematics, it's negative. We'll discuss why that is. But for the case in this scenario, it's falling down and acceleration is acting down, so acceleration is absolutely going to be negative here. So let's look at an example of this. The example says the following. Pitcher tosses a baseball upward along the vertical axis. By the way, another thing in your lab, a lot of yours I crossed off X and Y axis and I put vertical and horizontal. That's okay, I didn't really care much, but terminology-wise, let's stray away from X and Y axis now, because clearly our Y axis is never really the vertical component. It's like a position or maybe a force, right? So let's use the vertical axis and horizontal, or the dependent axis and the independent axis. Because when you have responses on the exam, your response verbally will also be graded at the end of the test when asking problems. So the terminology is important. So either dependent or vertical, or independent or horizontal for axis labels. All right, so a pitcher tosses a baseball up along the y-axis with an initial speed of 12 meters per second. So I'm already picturing this. Here's the baseball. It's launched up with an initial speed of 12 meters per second. Now, because it's thrown upward and the speed at 0 is 12 meters per second, what else is 12 meters per second? Again, because it's thrown upward. Londell? Initial velocity, very good. So the initial velocity is really equal to the initial speed because they're both acting in the same direction. Remember, velocity downward is negative, so that's what we have to account for that. So the problem says speed, but we as AP Physics students and scholars recognize, well, speed and velocity are the same if they're going in the positive direction, right? So we can leave that as VO. Now, the problem says the following. How long does it take for the ball to reach its maximum height? How long does it take to reach its maximum height? So what do we want it to do when it reaches max height? What happens, Chip? Yeah, the velocity at the top is indeed 0. So when it reaches here at the top, you can follow the path along the way. We know that V at that moment is definitely 0. So those are the two values that were given, and we want to know how long it takes. How long it takes. So what variable are we solving for clearly, everybody? What is it? Time. How long it takes. And we know the acceleration it's going to feel is negative 9.8 meters per second squared. Although it's not given in the problem, it's not given that we're on another planet, it's not given that we have any sort of air resistance, so our acceleration vertically will be negative 9.81. Okay? So it's a simple calculation for this one. Formula to use. We have 3 choices. Which one are we using here? Which one, Spence? How long does it take? It says. How long does it take? You can do that. What are you gonna do? Actually, tell me beyond that. Well, what's y in that case? Y. Y is. So you could use that, but think about it more. There's an easier way. You could use that.
I think I would use VF equals VI minus AT.
Yeah. So I'm going to start writing it in general form so you see it that way because that's what's written in your formula sheet. And then I'll start filling in and writing other stuff. So my goal here is to find time. Okay, so there's my expression for time. V minus V0 over A. And again, on the AP Physics exam, you're pretty much done at this problem. You're going to see that a lot of the problems for the end of the test, the 3 main ones, your answers are variables, and you end up leaving stuff that way. Now here we have numbers, so we plug them in. So we've got 0 minus 12 meters per second divided by negative 9.8 meters per second squared. Did you figure it out yet, Spence? Why can we use the equation y equals 1/2 AT squared or y equals V0 plus 1/2 AT squared? How come we could use that equation? Spencer started with that and I said no right away, but then like actually you can. He's right. He hasn't figured out why you can use that way.
What was the equation?
He said let's use y equals y0 plus v0t plus 1/2 AT squared. Like the standard equation that we start with position. How come you can use that if you wanted to? God bless you. Yeah.
Find the final position.
But we don't have a final position.
We need time for dinner.
Well, what is the final position? Let's talk about truncation and piecewise functions, like how we break things up. This problem, what am I looking at? I know I was thinking about shit. Max is looking at
What?
No, I'm thinking, So I'm only making sure. And you keep on looking over here. I'm like, is he seeing this? It bothers me. You know when you have something on you and it bothers you? Sorry. Why can't we use that other equation here? What's happening? I'm looking at this problem from where it's launched to when it stops at the top, right? So I'm truncating, breaking up the problem into only half of it, a piece of it. The problem continues.
Set it equal to 0. And
You
then
can
half-
set y equal to 0 to get the entire flight, and then take how much of that time? Half of that time. Again, with air resistance, everything is not perfectly symmetric. But what we'll notice is that with these problems, we can use this equation right here, and we can then say, all right, well, you know what? The time that we get as an answer here will be double the time, because to use this equation, the object has to be launched, return back to the ground, and end up back at ground level at y equals 0. So this would be 0, and so would this. They'd both be 0 in that case. So you can use this formula again, but the time you're going to get is the t total, and you want t max. By the way, that is something that's useful to start doing. I didn't do it as much last year, I don't think. Subscript with the word max or total is kind of useful for these problems. I'm looking for the time it takes to reach max height. It's going to happen so much. I'm sure it happens a lot already. So if I were to do it this way, though, again, there's no displacement because it goes all the way up, comes all the way down. How many answers am I going to get if I were to solve this equation? Matt? How come, Matt?
Because you're going to have to find the square. You have to find the square root, which gives the most positive and then you get an answer.
I guess, but that v0 has a value, so we're not going to just do a square root. What kind of equation is it? It is quadratic in t. This is quadratic in t, so it's got to be two solutions, right? One of those solutions is going to be t equals, come on, let's see who gets this stuff. One will be t equals
0.
Why? Why will one of these solutions be t equals 0?
Because
Go ahead, Max, yeah?
that's when it's at the 0 point.
Yeah, remember, when we're solving for time, we're trying to figure out the time that it's at ground level. Well, how many times is it at ground level? Once. In the beginning, before the problem has started, goes all the way up. As it's about to reach the ground, that's the other time you would get. So the answer you would get here, what would you do with it again?
Half it.
What would you do with it?
Half it.
Half it. Because again, we're trying to find the time to max height. Okay? So either way we want to approach this problem works. I don't even care what the number is. Do we have a value though? What do you got? 1.22. Okay, so this would be 2.44. Okay? That's part A of this problem. Let's take a look at part B. Let's slide this over a little bit more. Okay, you guys can see it still. Let's take a look at part B now. So those are both methods to solve part A. Either way you want to do it, you choose. So part B says the following. Part B says, determine the max height. Determine the max height. So Kara, you were kind of jumping ahead with your answer last time. So what am I going to do now to determine the max height in this problem?
Determine the max height. You divide that total answer by 2, and then you plug it into foreseen one of the equations to find y.
Okay. So take a look at this equation here. You're going to plug back in, but to this equation, not the first one. Because we want to find the max height. And the max height can be used, or can be found by using this formula right here. Right? If I want max height, well, I'm looking for y. The initial height was on the ground, so that's 0. The initial velocity is 12. The time it takes to get to max height is 1.22. And then I carry the rest of this over. Oops, I'm running out of room on my screen. Okay, that would be the maximum height right there. That's how you would figure it out. Because you're trying to figure out the height at what moment? At the moment that 1.22 seconds have elapsed. At the moment that 1.22 seconds have elapsed. Now, AP exam style, ready? You can do this too. You can take this value and literally, watch where I'm going with it, plug it in there, and you could get an algebraic solution. You could plug in v minus v0 over a in both of those spots there and get an algebraic solution for y. Does that make sense what I'm saying? Algebraic without numbers, yeah? Okay. So I would have a one-long equation. How else could I find that? Oh, sorry, I got questions first.
Is that like suggested that we do that?
That you plug in the expression? If a problem doesn't give you values, you have to by default. Now, personally, if I get an answer for part A and I'm confident in it, I'm probably going to use that number instead of plugging in. Because unless a problem asks for a generic or algebraic solution or find the max height in terms of V0, T, and A, well then I'd have to do it that way. But to be honest, Matt, on an exam, it is probably quicker to go right to the numbers if you don't need the algebraic solution in addition.
Just I feel like I think I'd make more errors plugging the variables in.
I think it is room for error for sure, but definitely practice because there are going to be problems when numbers aren't given.
Yeah.
So be ready to do that. Yeah.
I got this. I mean, I got the same answer twice using like two different equations. I used
Yeah. So there's another equation. Hold on one second. What did you get for your answer, Chip? 705 meters. 7.35 meters. Yeah, that wouldn't make sense. Sorry. 12 meters per second, right? So what was the other equation you would use? Because there is definitely another equation we can use here for this one, right?
I used
Go ahead.
v final squared equals v initial squared plus 2a. That should be delta.
Yeah, delta y or y. Yep, I'll use delta y in this case. Good call. So y0 happens to be 0, so that's going to drop off. But yeah, I absolutely use this one. Yep, you can definitely use it. Now, because you got the time in part A, it might be easier to use the other one, but it's kind of 6 1/2 dozen. It doesn't really matter here. So this becomes v squared minus v0 squared all over 2a equals delta y. Sorry. Yeah, that's right, yeah. So v0 or v final is going to be 0, so it's 0 minus 12 squared all over negative 19.6. Okay, and you'll get the same answer of 7.35 meters. Again, taking a look at how we can do this problem, two different parts in two different ways each. So what is this kind of insinuating? Why am I choosing this problem to choose, or why am I choosing this one to look at? This free fall is pretty easy, but I made sure the problem had these options.
To like show that there's multiple approaches.
Exactly right. Any problem, you're going to notice throughout here, not any problem, many problems may have multiple approaches. Okay, multiple approaches. The same goes for your test on Friday. Hey, when it's multiple choice, whatever way works for you works, right? Multiple choice, you don't have to show any work. So if I say, like, the position function is given by the following, determine velocity at this instant, or determine when the velocity equals 0, determine when it stops. You can use a derivative and set it equal to 0. Or, as Chip mentioned, you could use the axis of symmetry to find the maximum height of the vertex. If it's multiple choice, negative b over 2a, or the derivative set equal to 0, gives you the same answer. So you pick which way you want to choose as long as you take the method that actually gets to the right answer, right? Let me take a look at part C. How long does the ball take to reach a point 5 meters above its release point? How long does it take the ball to reach a point 5 meters above its release point? Page 28 in your text. Page 28. I'm using the sample question for you. So again, how long will it take the ball to reach a point 5 meters above release point? So what variable do I know in this problem?
Y.
Yeah. So y is 5 meters. Y0 is still 0 meters. We're starting at the ground. We still know that our initial velocity is 12 meters per second. And we still know that, sorry? How long does it take? Okay, so we've got all, oops, I did it again. I'm going to have to get used to not drawing the 1 there, sorry. So we're trying to find how long it takes, which is time, which is t.
Is it asking how long it takes to get initially, or is when
That's a
it's
great
at?
question. Spence, that was the guy follow. We're going to read our mind. So, how many times is it going to reach a height of 5 meters? Once, and then once. So 5 meters is midway through the flight, right? So that's exactly it. So we have to consider the fact that we're going to get 2 answers here. The problem in the text did not specify which, so you would give both answers. But then you would most likely be followed up with this question like, explain the significance of the 2 answers you got here or you yielded. Yep. Okay, so again, to see the motion of this, here's the object, here's the 5 meter mark. We know the max height is 7.35 meters, so we know that it's going to turn back around and go through that point twice. Okay, it's going to reach 5 meters twice, on the way up and on the way down. The only way we were able to guarantee that was because the max height was bigger than 5. What if I ask this question? At what time will it reach a height of 8 meters? Okay? Never, right? Because the max height was 7.35 meters. So keep in mind that this number was purposefully made lower than the max height so you can actually yield an answer. Had the max height been, again, like 4 meters, then you would never reach a height of 5 meters. Okay, let's go through the solution for this one. What equation am I going to use here? I'm trying to find time.
Y equals y0 plus b0 t.
We'll use plus the whole time and then yeah. Then we'll plug in the negatives when needed. Okay, so you were definitely, the only other formula we have with time is v equals v0 plus at. But that assumes we know the velocity at a height of 5 meters. Do we have the velocity at a height of 5 meters? Could we find it? So theoretically, we could find the velocity at 5 meters and then use v equals v0 plus at. But what I want to do 2 parts to a problem, when I can solve it all in one? Probably not, right? Can't think about that logically. So we plug in, let's see, 5 equals 0 plus 12t minus 4.9 t squared. Okay, it's a quadratic clearly, move the 5 over, negative 4.9 t squared plus 12t minus 5. You should, within 30 seconds, be able to solve this. Either, maybe I'm being honest with that time, either one of 3 things. 3 things. Quadratic formula. Don't complete the square. Do not complete the square. That's ridiculous. Quadratic formula. Graph it on a calculator and find the. Graph it on a calculator and find the zeros, x-intercepts. Whenever a function equals 0, you can do it that way. So, quadratic formula. Graph it to find the roots. Or if you have a quadratic program in your calculator, you can see the time of the exam. We're not talking about ABC, right? I wrote it freshman year with some of you, if you had me in class. So the quadratic program can really help you be quick. Plug in A, plug in B, plug in C, get your answer. On the SAT. What else could you have done? There's a 4th way, and it's not by finding the zeros on the graph. Prior to this line, if I use this line, what could I find? See, most people don't know this, which is crazy. Should be taught this in freshman year. I feel like I didn't mention this at some point. Actually, I did, because there's a video on my page, on this advert too. I know there's a video on that page. Chris?
The time where it's 5 meters.
But how would you do it is my question I'm saying. So prior to this line here, you have to find the zeros on a graphing calculator. The x-intercepts will give you the time. If you were to graph these this way, what would you do instead? Alright, so let me just point this out, because people forget about this. So if you ever were in doubt, you could do this. You could call this y1 and call this whole thing y2. And then what could you find? The intersection. Try it. Go ahead and do it. Go ahead and do it. Y equals 5 is this. And y equals 12t minus 4.9t squared is going to be something like, what the hell is it going to be? Negative, coming down, no initial height. T0 is going to be 0, we know that. Why am I feeling it's not going to intersect? It should intersect.
Oh, it's easy.
What does the graph of 12t minus 4.9t squared look like? So do they not intersect or they do? Yeah, duh, the horizontal. I'm like, you know what I was thinking of? I was thinking of this, Spence. That shape. And I'm like, they're never going to intersect. That's why. Thank you. So this is what you're going to see on your graph. This is going to be y2 in red, y1 is in blue. And if you find these two intersections, it's the same answer you'll get as finding the zeros of this function down here. So instead, you can do this again. So that's one way to do it. Or you can find the zeros of this function instead. So this is this one over here. And the zeros of that function are going to look like this. But the idea is that this and this is the same as this and this for the x-coordinate. Okay, remember, it's the x-coordinate that matters because we are plotting y as a function of time, and we're looking for time. So we're looking for when these are zeros for this equation, or when these two equations intersect. But the answers you get will be identical. There will be 0.53 and 1.9.
This second method didn't work.
What happened? Talk to me, Matt.
Did you find the zeros of that?
Remember, the second method, you find the intersection, not the zeros. So take a look. These are the two approaches. If you find the zeros, your zeros are going to be 0.53 comma 0, the zeros, the roots, or 1.9 comma 0. Whereas over here, the coordinate's going to have 5 as the y coordinate because what are we looking for? The time when they each reach a height of 5. But either way, the time is what matters. Okay? 0.53 is one answer, and 1.9 is the other answer. Doesn't matter which way you take it. But I want you to see that we just solved 3 different parts, 2 different ways each at the minimum. Again, you could have solved this with the program. You could also solve this with the quadratic formula. But if you don't want to make it equal to 0, just use the y-intercept, the y value, the y equals function, and find the intersection instead if you don't want to go further. And in this course, if it's a calculator active problem, you can solve it any way you like. So when you get to integration and derivatives that are tougher, you can use your calculator to do the work, provided you get to the set. Is that clear what I'm saying? So for a really complicated problem like this, what if I had this? Sine of x squared plus cosine 2x equals 4.5x plus e to the 2x plus 1. Here's my equation in the bottom right. You're going to want to solve this by hand? I'm not going to want to solve this by hand. Okay? No one's going to want to solve this by hand. You've got a double angle law. You've got a square inside the argument. You've got an exponential function and linear. You're not solving this by hand anytime soon. So how do you solve this? Put this in y1. Put this in y2. And find the intersection. And ask Jesus to find the intersection. So just graph, okay? Graph it in y1 and y2. This would be y1. This would be y2. Remember, one side of the equation is y1, and we want to find when it intersects or equals the other side of the equation. Okay? We're not going to probably get an example of this tough this year, but you'll have something for sure at some point in time that you're not going to want to solve by hand. Okay, so get used to finding either the roots, meaning the x-intercepts, or the intersection. I mean, what else could you do with this equation, just so we're aware? I want to make this clear. No, it's not just quadratics that we can only solve with the zeros. We could also, take a look please, take a look. We could also take this side of the equation, subtract it over to this side, and get a 0 over here now instead, and then use the roots again to find it. So this is not only just for quadratics. If you have cubic functions, quartic, quintic, any function, you can find the roots as long as it's set equal to 0. Because this was not set equal to 0, I would use the intersection method, or again, move the right-hand side over to the left-hand side, set it equal to 0, then use the 0 method, or the x-intersect method.
I think you answered this, but can I use my TI?
I don't recall Max. We gotta look it up. Or maybe you can Google it if you don't mind. I think it's okay. I'm pretty positive, Max, that it is. Because I remember looking at unacceptable calculators. I think it was only like Inspire or a CAS, where it's an analytical system that isn't allowed. we'll take a look. Okay, you have an 83 or an 84 though, an older one, and I have an anyway. So, but yeah, we should look at that because if you're going to use the 89 all year and you get used to using it, remember you should use it again. So let's look that up.
Solution that's negative 0.9.
Negative 0.09. Yeah. Like who's going to get that, right? You're not going to do it by hand. Now you can, but it'd be messy. All right, that's it for free falling. So I want you to get the idea that free falling involves motion vertically. Now, was this really a free fall problem from the beginning? From the beginning was a free fall problem. Where was the free fall problem from?
Second half of the.
You see what I'm saying here? So although this object was tossed upward, it became a free fall problem when it reached max height and started to drop with 0 VI or 0 VO. So keep in mind that free fall really has to do with just vertical motion under the acceleration of gravity. Okay, under the acceleration of gravity. It doesn't have to be V0 equals 0 if it's not dropped. But again, if you toss up and then halfway through the problem you start over, and now it's a free fall problem when it's dropped. Okay. All right, let me go into some test stuff now. I'm going to pause at this